Our galaxy is warping at its edges, bending out of shape, and something massive is pulling the entire structure sideways through space. A wave of gas 1,000 light-years tall is rippling through the disk right now. Ghost stars from a dead galaxy are orbiting inside our own, and at the center, a black hole that looks quiet today left scars across 160,000 light-years of space not long ago. If that pulls you in, subscribe, it means the world to us. We are going inside all of it. Let's begin. Look up at the night sky and you picture our galaxy as a flat, elegant disk. Clean, stable, orderly. That picture is wrong. Our galaxy is warping. The outer edges of the Milky Way are not flat at all. They curl. One side bends upward, the other side bends downward. Astronomers call this a galactic warp, and for decades it was treated as a minor quirk, a small deviation barely worth serious attention. Then better data arrived, and the quirk turned into something far harder to explain. Here is the scale of it. The Milky Way stretches roughly 100,000 light-years across. The warp does not appear at the center, where everything is dense and gravitationally locked. It appears in the outer disk, starting around 60,000 light-years from the core. Out there, the disk tilts by thousands of light-years above and below the galactic plane. If you could look at our galaxy edge on from a distance, it would look less like a dinner plate and more like the brim of a hat that someone sat on. For a long time, scientists assumed the warp was ancient, a leftover scar from some violent event billions of years ago, frozen in place. That assumption collapsed in 2019 when a team of researchers used data from over 13,000 pulsating stars called Cepheid variables to build the most accurate three-dimensional map of our galaxy's disk ever made. What they found stopped them cold. The warp is moving, rotating, spinning around the galactic center at a speed that means the entire outer disk is precessing, like a wobbling gyroscope. And it completes one full wobble, roughly every 600 million years. Something is actively driving it. An ancient one-time collision would leave a static scar. A moving, rotating warp means an ongoing force is at work. The leading suspect is the Large Magellanic Cloud, a satellite galaxy orbiting our own. Scientists believe it plunged close to the Milky Way, and its gravitational pull tugged the outer disk out of alignment. The warp we see today may be the galaxy still responding to that disturbance, the way water in a bowl keeps sloshing after you bump the table. But here is where it gets uncomfortable. The models do not fully agree. Some simulations reproduce the warp well when the Large Magellanic Cloud is included. Others suggest the warp predates that interaction, meaning something else. Possibly an older collision or a distortion in the dark matter halo surrounding the galaxy played a role we have not fully mapped yet. What makes this matter beyond pure geometry is what the warp tells us about the forces shaping our home. The Milky Way is not a stable, settled structure sitting peacefully in space. It is a dynamic system, still being pushed and pulled by gravitational forces from outside. The outer disk, where the warp is most severe, is also where star formation happens in unexpected patches, where gas clouds move in directions the flat disk model cannot predict, where our maps start to break down. We live roughly 26,000 light-years from the galactic center, well inside the stable inner disk. The warp does not threaten us directly, but it reveals something important. Our galaxy is far less rigid than it looks. The edges are soft, malleable, responsive to outside forces, and the force responsible for the warp may be doing something much bigger to the entire structure of the Milky Way. That part of the story starts with what is pulling us sideways through space, and the answer is stranger than the warp itself. Our galaxy is moving. Every galaxy moving in a direction and at a speed that took scientists years to fully accept, because the culprit hiding behind it is far closer than anyone expected. To understand the pull, you need to picture the Milky Way not as a fixed point in space, but as an object in freefall. Everything around us is tugging on the galaxy through gravity. The Andromeda galaxy pulls from one direction. The Virgo cluster of galaxies exerts a slow, steady drag from tens of millions of light-years away. But inside our own backyard, at a distance of roughly 160,000 light-years, there is a galaxy doing something that large neighbors rarely do. It is slamming into ours. The Large Magellanic Cloud is visible from the southern hemisphere as a faint smudge of light near the Milky Way. For most of modern astronomy's history, scientists treated it as a small, gentle satellite, a companion galaxy that had been quietly orbiting us for billions of years. Calm, predictable, subordinate. Then better measurements of its mass arrived. Scientists revised the Large Magellanic Cloud's mass upward, dramatically. It carries roughly 1/10 of the mass of the entire Milky Way, for a satellite galaxy that is enormous. And something that massive, traveling at the speed it is traveling, around 250 miles per second relative to our galaxy, does not just orbit quietly. It punches through the surrounding dark matter halo like a bowling ball dropped into a tank of water. As the Large Magellanic Cloud moves, it drags dark matter behind it in a dense trail called a wake. That wake has real gravitational weight. It pulls on the Milky Way's disk from behind, and because the mass distribution of our galaxy shifts in response to that pull, the entire galactic center is being dragged off its original position. Measurements confirmed in the past few years show the Milky Way's disk is being displaced by tens of thousands of light years from where the dark matter halo's center should be. The galaxy is, in a real physical sense, being yanked sideways. The core is off-center. The halo and the disk no longer share the same gravitational midpoint. This has a name: the reflex motion of the Milky Way. Scientists expected a small version of this effect, but the data revealed it running at a scale nobody had modeled correctly. The displacement is large enough that earlier measurements of how fast stars move across the galaxy were slightly wrong, because the reference frame everyone was using, the galactic center itself, was quietly drifting. Every map we made of stellar velocities before this was discovered carried a hidden error. Scientists are now going back through decades of data and correcting for it. And the wake the Large Magellanic Cloud leaves behind is doing something else. It is dragging stars and gas in the outer halo toward it. Stars that should be evenly distributed are clustering in one region of the sky, piling up toward the trailing gravitational shadow of an incoming galaxy. The Milky Way is not passively sitting in space. It is reacting, straining, deforming. Its very center is chasing a gravitational pull it cannot escape. And that same incoming galaxy, the one doing all of this, is also doing something to the structure underneath the disk, something that involves dark matter in ways that upend what we thought we knew about what holds our galaxy together. Most galaxies take billions of years to fall into another. The Large Magellanic Cloud is doing it now, and the Milky Way is feeling every step. When scientists talk about galaxies colliding, they usually mean events on timescales so vast they are almost impossible to feel as real. But the destabilization caused by the Large Magellanic Cloud is measurable today, in current data, in current star positions, in the current shape of the dark matter halo surrounding our galaxy. This is an active event, a slow-motion impact playing out across millions of years, and we are inside it. To picture what is happening, imagine the Milky Way surrounded by an enormous invisible bubble of dark matter. This halo extends far beyond the visible disk, possibly reaching out to 600,000 light-years in every direction. It is not solid. It is a diffuse cloud of particles we cannot see, but whose gravity holds the entire galaxy together. Every star, every cloud of gas, every spiral arm exists because that halo anchors it all. Now send the Large Magellanic Cloud through the outer edge of that halo. The incoming galaxy does not pass cleanly. It drags material with it. It compresses dark matter on the side it approaches, and stretches it on the side it has already passed. The halo, which should be roughly spherical, is getting deformed into an asymmetric shape, lopsided, heavier on one side than the other. Confirmed by multiple studies using Gaia satellite data, the dark matter halo of the Milky Way is measurably off-center right now. The densest part of the halo does not align with the galactic disk anymore. And because the halo's gravity is what sets the paths of stars across the outer galaxy, stars out there are moving on orbits that no longer match the predictions built on older, symmetric models. The ripple goes further. The Large Magellanic Cloud brings its own satellite galaxies with it. The Small Magellanic Cloud travels alongside it. Both systems are pulling streams of gas and stars behind them, feeding material into the Milky Way's halo through a structure called the Magellanic Stream. This stream stretches across nearly half the sky when mapped in radio wavelengths. It carries enough gas to fuel star formation for billions of years if it eventually falls into the galactic disk. And it is falling, slowly, measurably, but the destabilization runs deeper than shifting halos and infalling gas. Simulations published in recent years suggest the Large Magellanic Cloud's approach has also triggered vertical oscillations in the galactic disk itself. Stars above the midplane and below it are moving asymmetrically, bobbing in ways that have no explanation under standard models, without accounting for the incoming galaxy's gravitational disturbance. The disk is ringing like a struck bell, and the thing that struck it is still approaching. The Large Magellanic Cloud has not yet reached its closest point to the Milky Way. That closest approach is still in the future, estimated at roughly 2 billion years from now. What we are experiencing today is the early disturbance, the pre-impact pressure wave arriving ahead of the main event. What happens when something that massive actually arrives, and what it does to the structure underneath the galactic disk, is a question that takes us somewhere even deeper, somewhere that involves a force we still cannot directly see. At the heart of the Milky Way, buried behind dense clouds of gas and dust, there is a structure most people have never heard of. A rigid bar of stars, thousands of light years long, cutting straight through the galactic center like a rod. And it is spinning slower than physics says it should be. Most spiral galaxies, including ours, have a central bar, billions of stars arranged in an elongated, rotating structure that anchors the spiral arms. The Milky Way's bar stretches roughly 27,000 light-years from end to end. It rotates as a solid unit, sweeping through space at a speed astronomers call its pattern speed. For years, estimates of that speed were high. Models suggested the bar was rotating fast, completing a rotation in a relatively short cycle. Then more precise measurements arrived, and the number dropped significantly. The bar is spinning much slower than earlier data indicated. Closer to one revolution every 400 million years. That slowdown demands an explanation, because angular momentum in space does not simply vanish. Something has to be absorbing it. The leading answer is dark matter. Specifically, dark matter dynamical friction. Imagine you are swinging a paddle through water. The water resists. The resistance transfers your energy into the water, and the paddle slows. Now replace the paddle with a rotating bar of billions of stars, and replace the water with an invisible sea of dark matter particles surrounding the galactic center. The bar drags against dark matter as it rotates. Dark matter absorbs angular momentum from the bar. The bar slows down. This process is confirmed in principle by simulations, and the current measured spin rate of the galactic bar matches what you would expect if a dense dark matter halo is actively braking it. The slowdown is, in a strange way, direct observational evidence that dark matter exists exactly where our models say it should be. But the story carries a complication. The bar's rotation rate shapes the orbits of stars across the inner galaxy through a phenomenon called orbital resonance. Stars whose orbital period lines up with the bar's rotation period get locked into specific patterns of motion. They are pushed or pulled by the bar's gravity on each pass. Change the bar's speed, and you shift those resonance zones outward or inward, reshuffling which stars get trapped in which orbital patterns. Recent data from the Gaia satellite mapped the velocities of hundreds of millions of stars in the inner galaxy and found exactly those resonance patterns, shifted from where older models predicted. The shift matches the slower bar speed. The galaxy's stellar traffic is organized around a bar that has been quietly braking for billions of years. There is something quietly extraordinary about this. We cannot touch dark matter, see it, or detect it with any instrument that measures light, but its fingerprints are in the rotation rate of a bar of stars at the center of our own galaxy. It is slowing something enormous, and we can measure the slowdown. The bar does not just sit passively at the center, either. It drives gas inward. It shapes the spiral arms extending outward. Its gravitational influence stretches across tens of thousands of light years. If something is actively changing its rotation, the effects ripple outward into the broader disk. And in that disk, wrapped around the outer galaxy in a way that still confounds scientists, something enormous was discovered that no standard model of galactic formation had predicted. Wrapped around the outer edges of the Milky Way, like a ring around a planet. There is a vast stream of stars extending across 100,000 light years. It encircles the entire galaxy. It was discovered in 2002, named the Monoceros Ring after the constellation where part of it first appeared. In the data, and ever since its discovery, scientists have argued fiercely about what created it. The argument is still not settled. The ring is enormous. To picture it, imagine our entire galactic disk, a structure already 100,000 light years across, and then imagine a second, fainter structure wrapping around the outside of that disk like a halo at the equator. The Monoceros Ring sits at the outer disk's edge, made of stars and gas that are clearly distinct from the main galactic population. They are older in some regions, younger in others, and their chemical composition and motion suggest they do not belong to the native outer disk. Two camps of scientists have spent 2 decades pulling in opposite directions over this structure. The first camp argues the ring is the remains of a disrupted dwarf galaxy. A small companion galaxy fell into the Milky Way billions of years ago, got ripped apart by our galaxy's tidal forces, and its stars were scattered into a ring-shaped stream orbiting the outer disk. This explanation fits well with how tidal disruption events work. We have seen smaller versions of this process around other galaxies. The chemistry of some stars in the ring does resemble stars from satellite galaxies, rather than the native disk population. The second camp argues the ring is the outer disk itself, rippling. Instead of an external origin, they say the ring formed from disk material that was pushed and pulled into wave-like oscillations by gravitational disturbances, possibly the same disturbances that created the galactic warp. In this model, the ring is internal, a product of the disk responding to outside forces, warping and ringing in giant concentric patterns. Both models reproduce some features of the ring. Neither reproduces all of them. What makes the Monoceros Ring especially strange is that it appears to wrap around the galaxy multiple times in some maps. Stars at different distances and angles show the same chemical fingerprint, the same telltale mix of elements, suggesting they are all part of one coherent structure, even though they are separated by enormous distances. A disrupted galaxy would not necessarily do that. A disk oscillation might, but only under very specific conditions that models struggle to match exactly. Gaia data has added new layers of complexity. The satellite's precise measurements revealed that stars in the outer disk move in vertical wave patterns, bobbing above and below the galactic plane in rhythmic oscillations. Those waves extend to exactly the region where the Monoceros Ring sits. The two phenomena may be connected. The ring may be the visible crest of an oscillation in the outer disk triggered by a past gravitational disturbance. If that is true, the Milky Way's outer edge is far more dynamic than a flat, stable disk model would suggest. It is a system of waves and rings and ripples, all triggered by past and ongoing gravitational events. And those gravitational events leave evidence behind in a form far more dramatic than rings of stars. They leave streams. Our galaxy is a predator, and it is feeding right now. Across the sky, mapped in painstaking detail over the last 2 decades, there are rivers of stars stretching for hundreds of thousands of light years. Long, thin, curving trails of suns, each one dragged away from a smaller galaxy or star cluster that got too close to the Milky Way and paid the price. These are tidal streams, and they are the direct evidence that our galaxy has been consuming its neighbors for billions of years and has not stopped. The process works through tidal forces. When a small galaxy drifts close to the Milky Way, our galaxy's gravity does not pull it evenly. The near side of the small galaxy gets pulled harder than the far side. That difference in pull stretches the satellite like taffy. Stars on the front edge get left behind. Over millions of years, the satellite is dismantled. Its stars spread into a long arc following the same orbit the original galaxy traveled. That arc is a tidal stream. The most famous example visible in current data is the Sagittarius stream. A dwarf galaxy called the Sagittarius Dwarf Galaxy has been orbiting the Milky Way for billions of years, and every pass brings it closer to total destruction. It has already lost the majority of its stars. Its remnants spread in a vast loop across the sky, wrapping nearly all the way around the galaxy in 2 distinct trails, one above the galactic plane and one below. Astronomers have mapped it across hundreds of millions of stars. The stream is so large that pieces of it cross our region of the galaxy. Some scientists have estimated that a small percentage of stars in the outer Milky Way may originally have come from the Sagittarius dwarf galaxy. We may be surrounded by stolen stars. Beyond Sagittarius, Gaia data has revealed dozens of additional stellar streams. Each one is the ghost of a former satellite, a cluster, or a dwarf galaxy that the Milky Way pulled apart over billions of years. Some streams are ancient, their stars widely dispersed and chemically distinct. Others appear relatively fresh, their stars still tightly grouped, suggesting the disruption happened more recently in galactic terms. Each stream is a fossil record. The chemical composition of the stars inside it carries the fingerprint of the galaxy they came from. By analyzing that fingerprint, scientists can reconstruct properties of galaxies that no longer exist as intact structures. Entire galactic histories encoded in the orbits and chemistry of orphan stars still circling our galaxy today, and the feeding continues. The Large Magellanic Cloud and the Small Magellanic Cloud are on trajectories that will eventually bring them close enough for the Milky Way's tidal forces to begin the same dismantling process. The Magellanic stream of gas already trailing behind them is the first sign of that process beginning. Every great structure the Milky Way has, part of its mass, part of its chemical richness, part of its size, came from galaxies it consumed. The Milky Way is built, in part, from the remains of its victims. But what those consumed galaxies left behind in the outer disk is something far harder to see, and what the stars out there are doing with their motion is something the standard model of galaxy formation had no prediction for. Go far enough from the galactic center, out past 50,000 light-years, and the stars out there are moving in ways that nobody fully predicted. Their velocities are off. Their directions are wrong, and the deeper scientists look, the more the outer disk looks like a place where the rules are being quietly broken. To understand why this is strange, start with what we expect. Closer to the galactic center, stars orbit in roughly circular paths, all moving in the same general direction, dragged along by the combined gravity of everything inside their orbit. The system is orderly. The inner galaxy is well mapped, well understood in broad terms, but move outward and the orbits get messier. The Gaia satellite has now measured precise velocities for over 1 billion stars. When scientists looked at the outer disk populations in detail, they found vertical motions, stars moving up and down relative to the galactic plane, above it and below it, in patterns that spread across thousands of light-years. Stars in one region of the outer disk moving upward together, stars in an adjacent region moving downward, wave patterns running through the stellar population like a slow ripple through a pond. This is called the phase space spiral, or the Gaia snail, because when you plot the positions and velocities of stars in the outer disk on a specific type of graph, they arrange into a spiral pattern, a snail shell shape made of 100 million suns. The snail is a ringing. The outer disk was struck by something, and the stellar population is still oscillating from the impact, the way a drumhead keeps vibrating after the stick pulls away. Based on the shape and tightness of the spiral pattern, scientists estimate the disturbance happened roughly 500 million to 2 billion years ago. The uncertainty in that range is still being worked out. The prime suspect is a past close passage of the Sagittarius dwarf galaxy. Every time the Sagittarius dwarf loops through the galactic disk on its long orbit, it punches through the plane and sends a gravitational shockwave through the stellar population. The stars ring. The ring evolves into the spiral pattern over time. The Gaia snail may be the direct fingerprint of a satellite galaxy's passage through our disk, frozen in the positions and velocities of stars we can measure today. If that is confirmed fully, it means the outer disk carries a readable record of every major gravitational disturbance it has experienced. Every satellite passage, every close flyby, every impact leaves a pattern in the star velocities that persists for hundreds of millions of years. The outer disk is in a sense a memory, but the unexpected vertical motions are only part of the strangeness. Stars in the outer disk also show unusual patterns in their radial velocities, moving toward or away from the galactic center at speeds that do not match the simple circular orbit model. Some regions show systematic inward flows, others show outward streaming. The outer disk is kinematically disturbed in multiple directions simultaneously. Getting to the bottom of what caused all of it requires looking at something moving at extreme speeds, something launched directly from the galactic center at a velocity so high it will eventually leave the galaxy entirely. Something at the center of the Milky Way is launching stars, full, massive, burning suns, fired outward at speeds of up to 2 million miles per hour, fast enough to escape the galaxy entirely, fast enough to cross the distance from here to the galactic center in about 100 million years, and then keep going, out into the void between galaxies, forever. These are called hypervelocity stars, and their existence tells us something about the violence happening at the very heart of our galaxy. The mechanism behind them involves the central black hole, Sagittarius A star, the supermassive black hole at the Milky Way's core, has a mass 4 million times greater than our star. When a binary star system, two stars orbiting each other, wanders too close to it, the black hole's tidal forces can split the pair apart. One star gets captured into a tight orbit around the black hole. The other gets flung outward with the energy that was stored in the binary system's orbit. The ejected star can reach escape velocity from the galaxy. A physicist named Jack Hills predicted this mechanism in 1988. The first confirmed hypervelocity star was discovered in 2005. Since then, dozens have been identified, and with Gaia data, the catalogue has expanded significantly. But here is where the story complicates. When scientists map the trajectories of hypervelocity stars backward through space, trying to trace where they came from, many do trace back toward the galactic center. That supports the Hills mechanism cleanly. But some of the fastest moving stars in the outer galaxy do not trace back to the center. Their origin points are scattered. They appear to have been accelerated somewhere else, possibly through near collisions with massive stellar clusters, or through rare encounters with intermediate mass black holes lurking in the halo. One particularly dramatic example discovered using Gaia data is a star that appears to have originated in the Large Magellanic Cloud, gained a tremendous kick from the black hole at that galaxy's center, and is now screaming through the Milky Way's outer halo at a speed that will eventually carry it clear of both galaxies. A star from another galaxy, passing through ours, on its way to intergalactic exile. The confirmed ones we have found, moving fast enough to escape the Milky Way, are called unbound stars. They are no longer gravitationally tied to the galaxy. They are already leaving. By the time they reach the outskirts, they will have traveled for millions of years through the galactic disk and halo. Everything they pass through carries gravitational information about the Milky Way at the moment of their launch. Scientists are now using the trajectories of hypervelocity stars as probes of the dark matter distribution across the galaxy. The path a star takes on its way out is bent by every concentration of mass it passes. Mapping those paths in high precision can reveal the shape of the dark matter halo in regions too distant and sparse to study any other way. The galaxy is ejecting its own stars, and the same region responsible for those ejections, the galactic halo surrounding the entire disk, is itself hiding something unexpected about its true scale and what is happening deep inside it. Beyond the spiral arms, beyond the visible disk, beyond even the outermost stars we can track, there is a structure so enormous that the galaxy we see with our eyes is just the dense core sitting at its center, the galactic halo, and recent measurements suggest it extends far further than anyone had calculated, and something inside it is keeping it hotter than physics alone should allow. Picture the Milky Way's disk as a single coin sitting on a table. The halo surrounding it would be a balloon inflated around that coin, extending outward in every direction. Early estimates place the halo's outer boundary at roughly 300,000 light-years from the center. Newer data, particularly from studies of how satellite galaxies orbit and how intergalactic gas interacts with the halo's edge, pushes that boundary closer to 1 million light-years, possibly further. At that scale, the halo is larger than the distance to the Andromeda galaxy, our galaxy's invisible outer envelope, and Andromeda's invisible outer envelope may already be touching. The halo is not empty. It contains a diffuse population of old stars, many of them moving on highly elliptical orbits that carry them looping far above and below the galactic plane. It contains the tidal streams left by consumed satellites, and it contains hot gas, a thin but extensive atmosphere of ionized plasma surrounding the entire galaxy. That hot gas is a problem. Gas at the temperatures observed in the halo, reaching up to millions of degrees in some measurements, should radiate its energy away and cool over time. The cooling timescale, the time it would take for the halo gas to lose enough heat to collapse, is shorter than the age of the galaxy in many models. The gas should have cooled long ago. It has not. Something is heating it continuously. Several mechanisms are proposed. Supernova explosions in the disk can drive hot gas outward into the halo, adding fresh energy. Feedback from the central black hole, outbursts of radiation and particle jets from Sagittarius A star during active periods, can push energy into the halo across enormous distances. The infall of the cosmic web, the streams of gas that feed the Milky Way from the broader universe, can shock heat material at the halo boundary. All of these contribute, but whether their combined energy input is enough to maintain the observed temperatures consistently remains an open question. Confirmed heating sources exist. Whether they are sufficient is, as of the most recent models, still actively debated. What is confirmed is that the halo is a dynamic region, constantly gaining and losing material, being shaped by forces from both inside the galaxy and outside it. It is the membrane between the Milky Way and the broader cosmos, and it is neither quiet nor stable. At the very center of the galaxy, above and below the disk, there is a structure in the halo that was discovered only in 2010 and has defied confident explanation ever since. Two colossal structures, each taller than the distance from here to the galactic center, glowing in gamma rays, and they should not be there. In 2010, a team analyzing data from the Fermi Gamma Ray Space Telescope found something that should not have been there. Two enormous structures, one above the galactic plane and one below it, extending 25,000 light-years in each direction from the galactic center. Colossal lobes of gamma-ray emitting gas, perfectly symmetric, anchored at the galactic core. Together they span 50,000 light-years from tip to tip, roughly half the width of the entire galaxy. They are called the Fermi bubbles, and despite 14 years of observation and modeling, their origin remains genuinely contested. To picture their scale, imagine the Milky Way's disk as a highway. The Fermi bubbles would be two enormous mushroom clouds rising above and below that highway. Each one taller than the entire highway is wide. They are vast enough to have their own internal structure. Their edges are sharp, unusually so for a gas structure this large. The boundary between the bubble and the surrounding halo material is almost like a wall. Sharp edges in gas structures mean high energy. They mean the bubbles are either still being actively inflated or were inflated so recently that they have not had time to blur at the edges. The two leading explanations divide scientists into camps, and both camps have evidence on their side. The first explanation points to Sagittarius A star. Our central black hole, currently quiet, may have undergone a massive outburst millions of years ago. During such an event, called an active galactic nucleus phase, the black hole could have launched powerful jets of plasma perpendicular to the galactic disk. Those jets would push into the halo, inflate the bubbles, and then fall quiet, leaving the structures behind like exhaust strings from a rocket that has shut down. This model explains the sharp edges well. It also aligns with evidence, discussed later, that the galactic center was significantly more active in the past. The second explanation points to a period of intense star formation near the galactic center, a starburst event, during which thousands of massive stars exploded as supernovas in a relatively short time. The combined energy of those explosions could have driven a massive outflow of hot gas into the halo, inflating the bubbles from below. Starburst-driven outflows are observed in other galaxies and produce structures similar to the Fermi bubbles in shape. Both mechanisms may have worked together. Some models suggest the starburst came first, blowing open a channel, and then a later active period from the central black hole pushed additional energy through that channel. The bubbles might be a layered record of two separate violent events. What is confirmed is that the bubbles are real, energetic, and connected to the galactic center. What remains unknown is exactly which mechanism built them. and whether the process that inflated them has truly stopped. One finding adds a sharper edge to the mystery. Embedded within the Fermi bubbles, visible in a different wavelength of radiation, are two additional structures called the Erosita bubbles, discovered in 2020, larger than the Fermi bubbles, extending even further from the galactic plane, and glowing in X-ray light. They appear to surround the Fermi bubbles like a second shell, suggesting at least two distinct energy events shaped this region. Two shells, two possible origins, and at the center of it all, a black hole with a history far more violent than its current silence suggests. Every image of a spiral galaxy shows the same satisfying pattern, arms curving outward from the center, in elegant symmetric loops, one mirroring the other like the blades of a pinwheel. Our galaxy is supposed to look like that. It does not. The Milky Way's spiral arms are asymmetric. The structure on one side of the galaxy does not mirror the structure on the other. The arms have different lengths, different densities, different star-forming properties depending on which segment you are examining. And because we are embedded inside the disk, mapping this properly took decades of work and still carries significant uncertainty. The galaxy has four major spiral arms. They are named the Norma arm, the Scutum Centaurus arm, the Sagittarius arm, and the Perseus arm. Our location sits between the Sagittarius arm and the Perseus arm, in a smaller partial structure called the Orion arm or the local arm. For most of the 20th century, models depicted these arms as roughly symmetric, curving outward at similar angles and pitches. Precise radio telescope mapping changed that picture. Different spiral arms have different pitch angles, the angle at which they curve away from the center. Some arms are longer than others, extending further before breaking up into fragmented segments. Some regions of the arms are rich with young, massive stars and dense gas clouds. Other regions of different arms at the same galactic radius are quieter, more diffuse, with less active star formation. The Perseus arm on the outer side of our location is one of the most prominent structures in radio maps. The Sagittarius arm on the inner side shows massive star-forming regions clustered unevenly along it. Gaia data, combined with radio surveys, has revealed that even individual arms contain substructures, spurs and branches that break off the main arm and curve outward, some of them hosting intense bursts of star formation before fading. The asymmetry is real and confirmed. The question is why? Spiral arms are density waves, regions where gas and stars pile up as they orbit the galaxy, like cars slowing and bunching on a highway around a slow section of road. The pattern rotates at its own speed, different from the speed of the stars themselves. Stars move through the arm, slow down briefly in the denser region, then continue out the other side. The arm pattern persists even as individual stars pass through it. If that pattern were perfectly symmetric, the arms would mirror each other. The fact that they do not suggests the density wave pattern has been disturbed. External gravitational forces from satellite galaxies, the same forces driving the warp and the oscillations in the outer disk, may be deforming the spiral pattern itself. Past mergers could have added material unevenly to different sides of the disk, seeding more active star formation in some arms than others. The asymmetry means our galaxy's most iconic feature, the feature that makes it a spiral galaxy, is itself a product of violent history and ongoing disturbance. And running through one of those arms, discovered only in 2020, there is a structure so large and so geometrically perfect that its existence raises a question science has not yet fully answered. In 2020, a team of astronomers announced the discovery of a structure running through the nearby galactic disk that nobody had seen coming. They called it the Radcliffe Wave. It is a connected, undulating chain of gas clouds and star-forming regions, stretching nearly 9,000 light-years in length and oscillating above and below the galactic plane in a wave pattern with a crest height of roughly 500 light-years above and 500 light-years below the midplane, 1,000 light-years from crest to trough. And it is moving. To appreciate what makes this discovery startling, consider that the Radcliffe Wave runs directly through our cosmic neighborhood. The solar system sits close enough to this structure that several of the most famous star-forming regions visible from Earth, regions like the Orion molecular cloud, are part of it. The wave we are talking about is so nearby that pieces of it show up in observations that predate its identification by decades. It was hiding in plain sight, visible in fragments, but its full connected shape was only revealed when researchers built a three-dimensional map of gas clouds, close enough to measure precisely. The wave is not static. Follow-up studies confirmed it is oscillating. Gas clouds along its length are moving vertically, rising and falling in a coordinated pattern, suggesting the whole structure is physically traveling like a wave on water. The estimated period of that oscillation, the time it takes for the wave to complete one full up and down cycle, is roughly 100 million years. What created it is an open question. Several mechanisms have been proposed. One suggestion is that the wave is a bending instability in the galactic disk, a kind of buckling that forms naturally in thin, rotating disks under certain conditions. Another proposal involves the impact of a high-velocity gas cloud falling into the disk from the halo above, sending a ripple propagating through the nearby gas layer. A third possibility is that it relates to the same external gravitational disturbances responsible for the warp and the Gaia snail, a broad-scale ringing of the disk triggered by a satellite passage. None of these explanations has achieved full consensus. Confirmed so far, the structure is real, it is connected, and it is in motion. The origin is genuinely unresolved. What makes this particularly striking for anyone thinking about Earth is the proximity. Our solar system passed through or near parts of this structure within the last 100 million years. The regions of the Radcliffe Wave that were active star-forming sites in the past produced massive stars that exploded as supernovas. Those explosions shaped the local interstellar environment, carved out cavities in the gas, and may have influenced the flow of cosmic rays reaching the inner solar system over geological timescales. A wave in the galaxy affected conditions in our cosmic neighborhood, and that neighborhood, it turns out, sits inside a structure of its own that shapes what the solar system has been swimming through for millions of years. But before getting there is a region far closer to the galactic core, where conditions are so extreme they challenge everything we know about how stars form and survive. And something at the very center of that region just woke up. Point a radio telescope at the center of the Milky Way, and the data coming back reads like a war zone. Magnetic fields twisted into vertical filaments running perpendicular to the galactic plane. Shock waves tearing through clouds of dense gas. Young, massive stars forming in an environment so turbulent and radiation-soaked that standard models of star formation say they should not exist there. And threading through all of it, a level of organized chaos that suggests the galactic center is not simply violent, it is violently structured. The region is called the Central Molecular Zone. It spans roughly 1,000 light-years around the galactic core and contains a mass of gas equal to tens of millions of times our star's mass, compressed into a region that is dense, hot, and permeated with magnetic fields thousands of times stronger than those in the outer disk. In the outer disk, gas clouds cool, collapse under their own gravity, and form stars in a relatively straightforward sequence. In the Central Molecular Zone, the turbulence is so extreme that gas clouds are constantly being shredded before they can collapse. The temperature of the gas is far higher than it should be for quiescent molecular clouds. The magnetic fields are strong enough to resist the very gravitational collapse that produces stars. And yet stars form there anyway. The galactic center hosts young, massive star clusters, born in the last few million years. The Arches cluster and the Quintuplet cluster each contain some of the most massive stars known in the entire galaxy. They are sitting in an environment that should have prevented their formation, and they formed there recently enough that they have not yet moved far from their birthplaces. How this happens is an active area of research. One mechanism involves tidal compression. Gas clouds falling toward the galactic center get squeezed by the tidal forces of the central mass concentration, becoming dense enough to collapse and form stars, despite the turbulence. Another factor is the presence of highly organized magnetic structures. Instead of resisting star formation everywhere, the magnetic fields may be channeling gas into specific corridors where conditions are right. The vertical magnetic filaments themselves are remarkable. Hundreds of them have been mapped by radio telescopes, running in nearly parallel lines perpendicular to the galactic plane across the Central Molecular Zone. Each filament is a tube of magnetic field, maintained against the turbulent gas pressure around it. Their origin and what sustains their organization is still being actively studied. In 2000, a survey using the Meerkat radio telescope array in South Africa revealed the filament population was far larger than previously known, with thousands of shorter filaments in addition to the long ones. The galactic center is threaded with magnetic structure on scales ranging from a few light years to hundreds of light years. Sitting at the middle of all this, powering some fraction of it, is the central black hole, currently quiet by the standards of actively feeding black holes elsewhere in the universe. But evidence preserved in the gas and dust around it tells a different story about its recent past. Sagittarius A star is quiet right now. It consumes only a trickle of material compared to the feeding frenzies seen in black holes at the centers of other galaxies. Watch it for years, and it barely flickers. But scattered through the gas clouds surrounding the galactic center, there is evidence that this quietude is recent, and that just a few million years ago, the central black hole was dramatically more active. The evidence comes from a phenomenon called X-ray reflection. Dense gas clouds near the galactic center are glowing in X-rays. When scientists analyze the specific pattern of that glow, it does not match the pattern you would expect from a cloud simply producing its own X-rays. It matches the pattern of a cloud reflecting X-rays from an external source, specifically an extremely bright X-ray source that illuminated these clouds in the past and whose light is only now reaching the outer clouds after bouncing inward off the nearer ones. The geometry of the reflection, combined with the brightness of the echo and the light travel distances involved, points to a major outburst from Sagittarius A star, roughly 2 to 6 million years ago. During that event, the black hole was emitting X-rays at a rate roughly 1 million times greater than its current output. For a cosmically brief period, our galaxy's center was lit up in a way that would have been visible as a brilliant point of hard radiation, pouring energy into the surrounding gas. The Fermi bubbles, the enormous gamma-ray structures above and below the galactic plane, may be connected to this same event. If the outburst was energetic enough, and if it included jets of plasma driving outward along the galaxy's rotation axis, those jets could have inflated the bubbles over millions of years. The timing is consistent. The energy scales are consistent. Whether the outburst and the bubbles are cause and effect is, based on current modeling, considered likely but not yet fully confirmed. 2 to 6 million years ago is recent on galactic timescales. It falls within the period when early human ancestors walked the Earth. The galaxy's center was in a dramatically different state, while hominids were developing on a small planet in the outer disk. More striking still is evidence for an even older, more energetic event. A flare from the galactic center around 3.5 million years ago has been linked to a phenomenon observed from the Magellanic Stream. A section of that gas stream, far outside the galaxy, shows ionization patterns that require an ultraviolet flash enormous enough to reach 160,000 light-years from the galactic center. A flash from Sagittarius A star that reached across intergalactic distances. This event has been called the Seyfert flare by the scientists who proposed it. It remains a theory, supported by the ionization evidence, but debated in its specifics. Confirmed is the X-ray reflection evidence for a major outburst in the past few million years. The Seyfert flare, if real, would represent an even more extreme period of activity before that. The black hole that sits at the center of our galaxy is sleeping now, but it has woken up before, dramatically, and the structure of the Milky Way carries the scars. Going further back into the galaxy's past, the violence gets older and stranger, and the evidence points to a collision so severe it changed the fundamental shape of everything we live in. About 10 billion years ago, the Milky Way was smaller, less massive, still building itself from the raw material of the early universe. And then it ran into something large enough to reshape it fundamentally, a collision whose consequences are still written into the structure of the galaxy we live in today. The evidence for this event comes from the Gaia satellite. In 2018, scientists analyzing the velocities and chemical compositions of stars in the inner halo discovered something unexpected. A large population of stars was moving on highly elongated radial orbits that carry stars far from the galactic center, and back again in long looping paths, rather than the roughly circular orbits typical of disk stars. These radial orbit stars had a distinct chemical signature, lower in heavy elements than disk stars of the same age, suggesting they formed in a different, smaller galaxy where heavy element production had not yet advanced as far. The conclusion? These stars were originally part of a satellite galaxy that merged with the Milky Way roughly 8 to 10 billion years ago. A large satellite, massive enough that the merger was violent and transformative. This ancient galaxy was given a name, Gaia Enceladus, sometimes called the Gaia sausage, due to the sausage-shaped distribution of its star's velocities when plotted on a specific kind of diagram. The mass of Gaia Enceladus at the time of the merger is estimated to have been roughly 1/4 of the Milky Way's mass at that point. The impact was dramatic. Material from the infalling galaxy was dispersed throughout the inner halo. The collision may have triggered a burst of star formation in the early Milky Way disk. The energy of the merger may have heated and puffed up what is now called the thick disk, the slightly inflated older stellar population that sits above and below the thin disk where most of the galaxy's recent star formation has occurred. The merger may also have fundamentally restructured the halo itself. The prominent inner halo population of radial orbit stars, the Gaia Enceladus debris, makes up a significant fraction of the stellar mass within about 60,000 light-years of the center. This debris is old enough and dispersed enough that it is spread through the inner halo as a diffuse, ancient population, invisible as a distinct stream but detectable through the chemical and kinematic fingerprints of its stars. Before Gaia, this merger was not known. The stars were there, always visible, but their common origin was invisible without the combination of precise velocity data and chemical analysis that only became available in the last decade. The Milky Way we live in was shaped by a collision we only discovered 8 years ago. The thick disk, the heated inner halo, possibly even the disk's current scale, all carry the imprint of that ancient impact. And the aftermath left something even more remarkable buried inside the galaxy. Stars from a dead galaxy still orbiting inside our own, their origin preserved in elements forged in a world that no longer exists. Gaia Enceladus is gone as a galaxy. It has no boundary, no center, no coherent structure. It was torn apart and absorbed 10 billion years ago, but its stars are still here, orbiting inside the Milky Way, moving through the same space we occupy, and the Gaia satellite found them. These stars are sometimes called Enceladus stars, or inner halo debris. They are not grouped together visually. If you looked up at the night sky and tried to spot them by eye, you would not find them. They are scattered widely through the inner halo, mixed among native Milky Way stars, indistinguishable in appearance. The only way to identify them is by measuring two things simultaneously: their exact motion through space and the specific mix of chemical elements they contain. Motion tells you the orbit a star follows. Stars from a disrupted satellite follow orbits that retain the memory of how the satellite fell in. They have radial, elongated orbits that plunge deep toward the galactic center and swing far back out. Native disk stars follow roughly circular paths at the same distance from the center. The difference is measurable with enough precision. Chemistry tells you where the star was born. Stars that formed inside Gaia Enceladus formed in a smaller environment with a slower chemical enrichment history. They contain lower ratios of certain alpha elements, oxygen, magnesium, silicon, relative to iron, compared to Milky Way disk stars of the same age. The ratio is a clock, encoding the rate at which a galaxy produced heavy elements before the star formed. Together, orbit plus chemistry, the Gaia Enceladus stars announce themselves clearly in the data. And they are numerous. A significant fraction of all stars in the inner halo carry this signature. The debris of one galaxy constitutes a major structural component of another. This discovery reshapes how we understand what the inner halo is. For decades, it was described as a native component of the Milky Way, stars formed from the original material that would become our galaxy. The Gaia data revealed that a substantial portion of the inner halo is imported material, debris from a foreign galaxy absorbed so long ago that it has orbited the Milky Way many thousands of times since the collision. The discovery also raised a question that grew more interesting the more scientists pushed on it. If Gaia Enceladus was this massive and left this much debris, what about other mergers? Are there other ancient galaxies embedded in the halo, waiting to be identified by their orbital and chemical signatures? The answer appears to be yes. Several additional merger events have been proposed based on Gaia data, including a structure called Sequoia, a smaller satellite that may have merged with the Milky Way around the same time or slightly earlier than Gaia Enceladus, and a structure called Thamnos, another ancient merger remnant orbiting in the inner halo on a distinct set of orbits. The inner halo may be a graveyard of ancient galaxies, each one identified by nothing more than the memory encoded in the motion and chemistry of stars that have been orbiting for 10 billion years. But what Gaia revealed about the inner halo was only part of its story. Looking at the full galactic disk, with that same precision, the satellite found something in the structure of the disk itself that had been hiding in plain sight. Something tilted. The Milky Way has a disk. One disk. That is the foundational picture. A flat structure of stars, gas, and dust, rotating around the galactic center, containing the spiral arms, the star-forming regions, everything we identify as the body of the galaxy. But analysis of Gaia's satellite data has produced results that challenge that picture in a quiet and deeply strange way. There appears to be a second population of stars in the inner galaxy, forming a structure that is kinematically and chemically distinct from the standard disk, and tilted relative to it. Researchers have called this component the Milky Way's inner stellar disk, or in some analyses, a proto-galactic disk, a relic of the galaxy's early formation that survived the merger with Gaia Enceladus, and now sits embedded within the larger structure at a slight misalignment. The evidence comes from a careful separation of stellar populations in Gaia data, combined with spectroscopic surveys that measure chemical abundances. When scientists divide inner galaxy stars by their orbital properties and chemical composition, two distinct groups emerge. One group follows the orbits and chemistry of the standard thin and thick disk. A second group follows orbits that are more radial, more tilted, and shares a chemical composition suggesting it is extremely old, possibly predating the Gaia Enceladus merger. This second group's orbits are not random. They cluster in a configuration suggesting they belong to a coherent, ancient disk structure that has been dynamically disturbed but not completely destroyed. The merger with Gaia Enceladus may have tilted this ancient component relative to the plane that later disk formation settled into, leaving it sitting at an angle inside the galaxy. If confirmed fully, this would mean the Milky Way has, in its interior, the fossil remains of an original proto-galactic disk, a structure that formed in the earliest stages of the galaxy's assembly, billions of years before the spiral arms and the thin disk we know today. Orbiting now, tilted slightly, surrounded by all the stars that formed afterward. The physical implications are significant. A tilted inner component would exert a gravitational torque on surrounding populations. It could contribute to the observed asymmetries in the inner galaxy's stellar velocities. It could influence the dynamics of gas near the galactic center in ways that have not yet been fully modeled. And it changes the story of our galaxy's origin. The Milky Way did not form as one coherent disk that simply grew with time. It assembled from multiple components, merging, tilting, layering. The clean disk we see today is a late-stage outcome, built on top of a more complicated foundation. What makes this finding sit in a category between confirmed and theoretical is the difficulty of observational separation. Identifying a distinct structural component purely through the statistical properties of stellar orbits and chemistry, without being able to point to it directly in the sky, requires careful analysis and carries real uncertainty. Multiple teams have found consistent evidence for this ancient component. The debate is over its exact properties and how coherently it qualifies as a true second disk rather than a heavily heated and tilted remnant of the thick disk. The further scientists push into the galaxy's interior, the more layers they find, and the thing holding all of those layers together, the dark matter halo, is itself far stranger in its current shape than any model predicted. For most of modern astronomy, the dark matter halo surrounding the Milky Way was modeled as roughly spherical, maybe slightly flattened along the galactic plane, maybe mildly triaxial, stretched a little in one direction, but fundamentally symmetric, a smooth, invisible bubble anchoring everything inside it with equal gravitational pull in all directions. That model is wrong. The halo is lopsided, and we know what pushed it out of shape. The culprit is the Large Magellanic Cloud. As it travels through the outer halo on its inward trajectory, Its gravitational pull drags dark matter particles toward it. A dense wake of dark matter trails behind it through the halo, a gravitational shadow following the incoming galaxy like a bow wave. This wake is measurably denser than the surrounding halo material. And because dark matter makes up the vast majority of the Milky Way's total mass, a concentrated excess of it in one region of the halo shifts the overall center of mass of the galaxy. The galactic disk and the dark matter halo no longer share the same gravitational center. The halo's densest point, its effective center, by a distance that recent models estimate at tens of thousands of light years. The disk is sitting off-center inside its own halo. Confirmed through multiple independent lines of evidence, the positions and velocities of satellite galaxies orbiting the Milky Way do not match what a symmetric halo would predict. They show a systematic pattern consistent with a lopsided mass distribution. Stars in the outer halo at similar distances from the galactic center show different densities in different directions of the sky, more stars clustering toward the region where the dark matter wake is thickest. Even the proper motions of stars in the halo, measured by Gaia with exquisite precision, carry signatures of a gravitational center that is not where a symmetric model would place it. The practical consequence runs deep. Every measurement astronomers have made of the Milky Way's total mass relies on modeling how things orbit in the halo. If the halo is asymmetric, those orbital models carry hidden errors. Estimates of the galaxy's total mass, estimates of how much dark matter is present, and estimates of the escape velocity from the galaxy all need to be revisited with the asymmetric halo accounted for. There is a second consequence that stretches further into the future. As the Large Magellanic Cloud continues its inward approach, the asymmetry will grow, the wake will deepen, the offset between the disk's center and the halo's center will increase. The disk will be dragged further from the halo's gravitational midpoint. This is an ongoing process, not a past event. The lopsidedness of our galaxy is increasing right now, and all of that is happening against a backdrop of something else changing inside the galaxy. Something more gradual, more final, and in its own way more unsettling than any single disturbance. The Milky Way is running out of fuel. Our galaxy is one of the great star-forming spirals in the local universe. Tens of thousands of new stars ignite inside it every year, scattered through the spiral arms in clouds of gas compressed until gravity wins and fusion begins. That process has been running for over 10 billion years, and the data now shows it is slowing down. The Milky Way is dying, slowly, on a timescale measured in billions of years. But the decline is measurable, confirmed, and already underway. Star formation requires raw material, gas, dense molecular clouds of hydrogen and helium that collapse under gravity and heat until stars ignite at their cores. The Milky Way has a finite supply of that gas in its disk. Every star that forms consumes some of it. Every massive star that forms and then explodes as a supernova returns some material to the interstellar medium. But not all. Some gas gets locked inside stellar remnants. Some gets heated and ejected into the halo, lost from the disk's star-forming reservoir. Over billions of years, the total gas available for star formation decreases. The rate of star formation in the Milky Way peaked roughly 10 billion years ago, around the same time as the Gaia-Enceladus merger, which likely triggered a burst of star formation by compressing disk gas. Since then, the rate has been declining. Current estimates place the Milky Way's star formation rate at somewhere between 1 and 3 new stars per year, across the entire galaxy. That sounds productive, but it represents a significant drop from the galaxy's peak activity. Comparison with other galaxies of similar mass at different stages of evolution confirms this trend. Galaxies begin their lives as gas-rich star-forming machines. They consume their gas, lose it to outflows and feedback from massive stars and black holes, and gradually transition into gas-poor, passively evolving systems, dominated by old red and orange stars. This transformation has a name. Galaxies go red and dead. The Milky Way is early in that transition. Its gas reservoir is depleting, and the rate at which it replenishes from external sources, infalling gas from the cosmic web and from the Magellanic Stream, is lower than the rate of consumption. Models suggest that without significant new gas accretion, the Milky Way's star formation rate will decline to near zero within another 5 billion years. The galaxy will gradually shift from a blue, star-forming spiral to a red, quiescent elliptical-like structure, particularly after the eventual merger with Andromeda, which will consume much of the remaining gas in a final burst of star formation, before leaving a largely passive remnant. The stars existing today, our star included, are among the later generations of a galaxy past its most productive era. The great age of star formation in the Milky Way has passed. What we see in the night sky, the billions of bright points representing active fusing stars, is the legacy of a process that has already begun its long wind-down. But buried near the center of this aging galaxy, orbiting in tight clusters around the core, there are stars so old, they raise a question that cuts to the heart of our galaxy's origin story. Stars that appear older than the galaxy itself. Near the galactic center, orbiting in dense ancient clusters called globular clusters, there are stars that push the boundaries of what the Milky Way's timeline should allow. When astronomers measure their ages using stellar physics, comparing their luminosity, temperature, and chemical composition against models of stellar evolution, some of these stars come back with ages close to 13 billion years. A few measurements push uncomfortably close to the estimated age of the universe itself, around 13.8 billion years. The Milky Way, as a coherent galaxy, a structured disk with spiral arms, is thought to be around 10 to 11 billion years old in its current form. Its earliest components, the inner halo and the first globular clusters, began assembling from the cosmic dark roughly 12 to 13 billion years ago. So stars with ages near 13 billion years are not technically impossible. They would belong to the very first generation of star formation, the stars that formed from nearly pristine hydrogen and helium shortly after the universe emerged from its initial dark age. What makes some of these measurements troubling is the uncertainty in both stellar age estimates and cosmological age estimates. The age of a star is calculated from theoretical models of how stars evolve. Those models are robust, but carry error margins of several 100 million years, sometimes larger. The age of the universe carries its own measurement uncertainties, particularly given the ongoing tension in measurements of the Hubble constant, the expansion rate of the universe. When the error bars on ancient stars and the error bars on the universe's age overlap uncomfortably, astronomers pay attention. One globular cluster orbiting the Milky Way, designated Methuselah's star within it, produced an age estimate in earlier analyses that briefly exceeded the estimated age of the universe. Refined measurements brought it back to just within bounds, but only barely. The star is almost certainly among the oldest objects in the observable universe. These ancient stars carry chemical fingerprints of a universe that have not yet been enriched by many stellar generations. They contain extremely low levels of heavy elements, iron, calcium, the whole suite of elements built inside stars and scattered by supernovas over billions of years. They are chemically almost pristine, born from gas that was close to the original composition emerging from the Big Bang. Their existence raises a profound point about what we live inside. The Milky Way is not a uniform structure built in one era. Its outermost halo contains globular clusters formed before the galaxy's disk existed. The inner halo contains debris from ancient mergers. The disk contains stars of all ages, from 10 billion-year-old thick disk stars to stars still forming right now. The galaxy is a layered archaeological site, and the thing anchoring all of that layering, the invisible mass making up most of the galaxy's weight, has a story of its own that connects directly to one of the most fundamental puzzles in physics, a puzzle that shows up in the motion of every star in the disk. Every spiral galaxy spins. Stars orbit the galactic center, traveling in roughly circular paths at speeds determined by the gravity of everything inside their orbit. The further out you go, the weaker the central gravity, and the slower stars should move. That is what Newton's laws and Einstein's gravity both predict. And it is completely wrong. In the 1970s, astronomer Vera Rubin and her colleagues measured the orbital speeds of stars and gas in multiple spiral galaxies across a range of distances from each galaxy's center. The expectation was a velocity curve that dropped off with distance, matching the decline in gravitational pull from the visible mass. What she found was a flat curve, Stars in the outer regions of galaxies orbit at nearly the same speed as stars much closer to the center. The drop-off does not happen. The Milky Way shows the same pattern. Stars at 50,000 light-years from the center orbit at roughly the same velocity as stars at 20,000 light-years. Stars at 80,000 light-years orbit at nearly the same speed still. The rotation curve is flat, far out into the disk. The visible mass of the galaxy cannot explain this. The stars and gas we can see do not contain nearly enough mass to generate the gravity needed to keep outer stars orbiting that fast. Something invisible must be adding mass, specifically mass distributed throughout the galaxy, including its outer regions, not just concentrated at the center. A halo of invisible matter that extends far beyond the visible disk, with a density profile that exactly compensates for the drop in visible mass at large radii, producing the flat rotation curve we observe. This is the galactic rotation curve problem, and it is one of the strongest pieces of evidence for dark matter in the universe. The flat rotation curve of the Milky Way, confirmed across many independent measurements, demands the presence of a dark matter halo containing several times the total mass of all visible stars and gas combined. Dark matter makes up roughly 85% of the Milky Way's total mass. The stars and gas and dust and planets and everything visible account for only about 15%. Everything humanity has ever observed in this galaxy, every star catalogued, every nebula mapped, every planet found, represents a small minority of what is actually here. The nature of dark matter remains one of the biggest open questions in physics. Multiple candidate particles have been proposed over decades. Weakly interacting massive particles were a leading candidate for years and remain under active experimental search. Axions, primordial black holes, sterile neutrinos. Each proposal carries theoretical motivation, and each is currently without direct detection confirmation. No experiment has yet definitively caught a dark matter particle in a detector. What is confirmed is the gravitational effect. The rotation curve is real, the mass is there, it just does not interact with light. And some of the stars in our galaxy have been given such an extreme dose of that dark matter's influence that they have been flung completely free of it, sailing outward at velocities that will carry them beyond the galaxy forever. Stars that were born inside the Milky Way and are now permanently leaving it. Between galaxies there is almost nothing. The intergalactic medium is one of the emptiest environments in the universe. Gas so thin it barely qualifies as a gas. No dust, no light. Temperature swings so extreme that the physics of the void operates differently from anything inside a galaxy. And through this emptiness, there are stars. Single stars, traveling alone, expelled from their home galaxies, crossing the void on journeys that take billions of years. These are intergalactic stars, sometimes called intracluster stars when found between galaxies in a cluster, and the Milky Way has been contributing to their population for billions of years. The mechanism behind most of them is the same Hill's mechanism responsible for hypervelocity stars. A binary star system approaches the central black hole too closely. The black hole splits the pair, capturing one and launching the other at escape velocity. The launched star accelerates outward through the galaxy, passes through the halo, crosses the boundary where the galaxy's gravity no longer binds it, and enters the void. But the central black hole is not the only source. Close encounters between stars near the dense galactic center can produce gravitational slingshots that accelerate one star at the expense of another's orbital energy. Supernova explosions in binary systems can also release a companion star at high velocity if the exploding star suddenly loses mass, disrupting the orbit in a fraction of a second. Some intergalactic stars were never ejected individually. They arrived in the intergalactic medium as members of satellite galaxies that were tidally stripped and disrupted. As the satellite fell apart, its stars were scattered into the halo and beyond, some gaining enough energy from the tidal interaction to cross the escape threshold. Confirmed observations of intergalactic stars come primarily from galaxy clusters like the Virgo cluster, where a diffuse population of stars has been detected floating between the member galaxies, too old and numerous to have been formed in place. These stars, representing a significant fraction of all stellar mass in the cluster, are the accumulated debris of billions of years of galaxy interactions, mergers, and tidal disruptions. The The Milky Way's own ejected stars are harder to detect individually at intergalactic distances, but their predicted numbers are consistent with the populations seen in clusters. Our galaxy has been shedding stars into the void throughout its history, and will continue doing so. A star crossing the intergalactic void at hypervelocity is traveling for many millions of years in total darkness, with no nearby gas to compress into planets, no radiation environment resembling what we experience. If such a star had planets, those planets would experience a cosmos of almost absolute isolation. No neighboring stars close enough to see clearly, just their own star burning in an otherwise dark universe. The galaxy produces lonely travelers, and it is also permeated from center to edge by a force that is invisible to the eye but shapes every cloud, every star-forming region, every stream of charged particles moving through the disk, a force organized on scales that should not allow organization. Our galaxy is magnetized. From the dense core to the outermost reaches of the disk, a coherent magnetic field threads through the Milky Way, shaping the paths of charged particles, organizing gas into filaments, and influencing where and how stars form. The field is vast, it is structured, and the degree to which it maintains coherent organization across tens of thousands of light years is something physics is still working to fully explain. The galactic magnetic field is not strong in the way a laboratory magnet is strong. Its typical intensity in the disk is a few microgauss, millions of times weaker than a refrigerator magnet. But it operates over distances of tens of thousands of light years. The total energy stored in the galactic magnetic field across the full disk is enormous, comparable to the energy in cosmic rays and in the turbulent motions of interstellar gas. These three components, the magnetic field, cosmic rays, and turbulence, exist in a rough pressure balance that regulates the structure of the interstellar medium. The large-scale structure of the field follows the spiral arms. In the disk, the field runs roughly parallel to the arm pattern, looping around the galaxy in coherent segments. The direction of the field reverses between some of the spiral arms. In some arms, it points clockwise around the galaxy when viewed from above. In adjacent arms, it points counterclockwise. These reversals are confirmed in multiple arms, though the full reversal pattern is still being mapped, since our view from inside the disk is obstructed by dust and distance. What makes the organization of this field remarkable is how it persists against the forces working to destroy it. Turbulence in the interstellar gas should tangle and randomize a magnetic field over time. The differential rotation of the disk, where inner regions orbit faster than outer regions, should shear the field into increasingly small, disordered loops. Supernova explosions pump enormous energy into the local field, disrupting it violently on small scales. Yet the large-scale coherence survives. The mechanism sustaining it is called the galactic dynamo, a process in which the combination of rotation, turbulence, and the helical motion of gas in the disk continuously regenerates large-scale magnetic order from small-scale disorder. The dynamo converts kinetic energy, the energy of rotating and turbulent gas, into magnetic energy, replenishing the large-scale field faster than turbulence destroys it. The galactic dynamo is confirmed in concept. Its detailed operation, how exactly the field reversals form and are maintained between spiral arms, is an active area of research with competing models. In the halo above and below the disk, the field geometry changes. It develops a poloidal component, looping out of the disk plane in large arcs that extend into the halo before returning. These loops carry material and energy between the disk and the halo. The Fermi bubbles may be partly shaped and confined by these halo field structures. Near the galactic center, the field strengthens dramatically and becomes primarily vertical, running perpendicular to the disk, organizing the remarkable filament structures mapped across the central molecular zone. The field there is not a background influence. It is a dominant structural element, and nowhere in the galaxy is the magnetic field more entangled with extreme conditions than in the central molecular zone itself, where temperature, density, turbulence, and radiation reach levels found nowhere else in the Milky Way. Go to the innermost 1,000 light-years of the Milky Way, and you enter an environment so extreme that the rules governing the rest of the galaxy bend and break. The central molecular zone is a place of staggering density, temperature, and violence, and sitting inside it, unfolding right now is a level of activity that makes the outer disk look peaceful by comparison. The gas in the central molecular zone is hot. Molecular gas here reaches temperatures of several hundred degrees on average. In the outer disk, molecular gas in star-forming clouds sits just a few degrees above absolute zero. The reason for the extreme heating in the central molecular zone is debated, but leading explanations include the intense radiation field from dense stellar populations near the center, the dissipation of turbulent energy in shocked gas, and cosmic rays at densities far higher than in the outer disk, penetrating and heating clouds throughout the region. The density is extreme as well. The average density of gas in the central molecular zone is hundreds of times higher than in star-forming regions in the outer disk. Clouds that would be considered dense in the outer galaxy are merely average in the central molecular zone. Some compact regions near the core reach densities that trigger the formation of massive stars rapidly and continuously. Turbulence in the central molecular zone operates on scales that would tear apart the orderly star-forming structure seen elsewhere. Clouds crash into each other at velocities of tens of miles per second. Shock fronts propagate through the gas, heating it further, compressing it in some places, shredding it in others. The velocity dispersion of gas in the central molecular zone, the range of speeds at which different gas elements move, is an order of magnitude higher than in the outer disk. And yet star formation persists. Dense cloud complexes like Sagittarius B2, the most massive star-forming region in the entire galaxy, sit inside the central molecular zone and are actively producing stars right now. Sagittarius B2 contains enough gas to form tens of millions of stars and hosts complex organic molecules, including precursors to amino acids, detected through radiospectroscopy. The central molecular zone is, despite its extreme conditions, a chemically rich environment. The tidal forces near the galactic center play a critical organizational role. Gas falling inward along the bar structure settles into an elliptical ring of dense clouds, called the central molecular zone ring, or the 100-parsec ring, orbiting at the inner edge of the galactic bar. The tidal compression on this ring is intense, squeezing clouds to densities that can overcome the turbulent pressure and collapse into stars. Embedded in all of this is the black hole. Sagittarius A star sits at the exact center, surrounded by a cluster of young massive stars that should not have formed in such a gravitationally hostile environment. These stars are themselves evidence that the galactic center produces conditions we do not yet fully understand. And the behavior of this black hole over the past few thousand years has been producing something in the surrounding gas and dust that researchers only recently found a way to detect. Pulses, echoes, patterns in the radio emission from the galactic center that do not fit any obvious source. Our solar system does not sit in the average interstellar medium. We are inside a cavity, a region of space roughly 1,000 light-years across, where the gas density is far lower than typical, where the temperature of the diffuse gas is far higher than average, and where the magnetic field structure and cosmic ray environment differ measurably from what you would find in a denser part of the disk. This cavity is called the local bubble, and it was blown by supernovas. The evidence for the local bubble has been accumulating since the 1980s, when X-ray observations revealed that the space around the solar system glows faintly in soft X-rays. Soft X-rays are produced by hot, diffuse plasma. The source of that glow is a thin gas filling the local bubble at temperatures of around 1 million degrees, heated by the energy of past stellar explosions, and maintained at high temperature because the cavity's low density means the gas cools very slowly. The bubble's boundary is marked by a dense shell of gas and dust, the compressed material swept up by the original supernova blast waves. This shell is not perfectly spherical. The local bubble is elongated, shaped like a flattened irregular cavity, and it opens up at its top and bottom ends toward the halo above and below the disk. It is connected to other nearby bubbles blown by other supernova sequences, forming an interconnected network of hot, low-density cavities called the local chimney. Research published in 2002 pinpointed the source of the supernovas that formed the local bubble with new precision. Using three-dimensional maps of gas and star-forming regions, a team traced the positions and ages of young star clusters in the solar neighborhood back through time and identified a series of roughly 15 to 20 supernova explosions occurring between 14 million and 2 million years ago in a moving group of massive stars. These explosions, marching through the disk as the stellar group moved, carved out the cavity we now occupy. The solar system entered the local bubble relatively recently. For most of the past billion years, the solar system has been moving through different regions of the disk as it orbits the galactic center. It happened to drift into the local bubble somewhere between 5 and 10 million years ago, and currently sits near the inner wall of the bubble, close to the shell of compressed gas. The local bubble is actively star-forming at its edges. The compression of the shell has triggered the formation of young stars in the molecular clouds along the bubble's walls. Several of the nearest and most active star-forming regions, including the regions in Ophiuchus, Taurus, and Perseus, sit on the bubble's rim. The wave of star formation radiating outward from the local bubble's shell is a direct result of the same supernova explosions that cleared the interior. This means the solar system sits inside a region shaped by stellar death, surrounded at its edges by active stellar birth, in a cavity that influences the cosmic ray flux reaching Earth, the magnetic field structure in our immediate neighborhood, and possibly even the long-term climate history of the planet through variations in cosmic ray penetration. The bubble we live in is a product of stellar violence millions of years old. And nearby, in the same galactic neighborhood, something is producing radio signals from the direction of the galactic center that do not match any confirmed source. Signals repeating on timescales that rule out random noise and hint at something structured producing them. The galactic center is noisy in radio wavelengths, supernova remnants, pulsar winds, magnetars, hot ionized gas. All of it produces radio emission across a broad spectrum. Astronomers have catalogued thousands of radio sources in the direction of the galactic center over decades. But within the past few years, surveys with sensitive new arrays have started finding signals that do not match any of those established categories. Signals that are compact, highly polarized, and variable on timescales of weeks to months. Sources that appear briefly, fade, and sometimes reappear. These objects are currently grouped under the designation Galactic Center Radio Transients, and their nature is genuinely unknown. The key characteristics that separate them from known sources: their radio emission is highly circularly polarized, meaning the radio waves spiral in a consistent rotational direction, a property associated with coherent emission processes involving strong magnetic fields and energetic particles moving in organized patterns. Their variability timescales are too short for large extended structures and too long for the fastest known pulsar pulses. Their brightness temperatures, a measure of how intense the radio emission is relative to the source's apparent size, in some cases exceed what ordinary thermal emission can produce. Something coherent and energetic is generating them. Several candidate explanations have been proposed. One class of models involves unusual pulsars, highly magnetized, fast-spinning neutron stars, perhaps in configurations of magnetic field or viewing geometry, that produce the observed polarization and variability pattern. A second class involves magnetars, neutron stars with extraordinarily powerful magnetic fields that produce sporadic bright radio bursts observed in other contexts. A third possibility involves low-mass stellar flares from active stars producing coherent radio emission through plasma processes similar to those seen in stellar coronae. A fourth possibility, more speculative and not yet carrying strong observational support, involves the interaction of compact objects with dense gas streams near the galactic center, producing variable emission as the object moves through inhomogeneous material. Each of these models reproduces some observed properties. None reproduces all of them convincingly. What is confirmed is that these sources exist and are real. They are detected repeatedly by independent observatories. Their properties are internally consistent across multiple observations. The mystery is not whether they exist, only what they are. The galactic center is a place of such extreme conditions that novel phenomena occurring there would be genuinely plausible. Strong magnetic fields, extreme radiation, dense gas, a central black hole with a violent history. The combination of those factors creates an environment capable of producing processes that do not occur in the quiet outer disk. What the galactic center radio transients share with the broader theme of this story is the same underlying message. The Milky Way, examined closely enough, keeps producing features for which our models have no ready answer. The galaxy is more complex, more dynamic, and more surprising than its image as a stable, well-understood structure suggested. And all of that complexity is playing out while the Milky Way itself is on a trajectory it cannot alter, locked into a path through space that leads, billions of years from now, to an encounter with the largest galaxy in our neighborhood. Two galaxies are falling toward each other across 2.5 million light-years of space. The Milky Way and the Andromeda Galaxy, the two largest members of the local group, are approaching at roughly 70 miles per second. The collision is confirmed. The timeline is set. In roughly 4.5 billion years, these two galaxies will begin their merger, and nothing in the universe will stop it. The confirmation of the collision came in stages. For decades, astronomers could measure the Andromeda Galaxy's radial velocity, how fast it is moving toward or away from us along our line of sight. That measurement showed it approaching at a confirmed speed. But to know whether a true collision would occur, they also needed the transverse velocity, how fast Andromeda is moving sideways across the sky. A galaxy moving mostly sideways might swing past without a direct merger. In 2012, using years of Hubble Space Telescope observations tracking the slow shift of Andromeda's position against background galaxies, a team measured the transverse velocity for the first time. The result confirmed a nearly head-on collision. Andromeda is aimed almost directly at the Milky Way. The merger is inevitable. The collision will not feel like two solid objects striking. Galaxies are almost entirely empty space. The stars themselves are so small relative to the distances between them that direct stellar collisions during the merger will be extraordinarily rare. What happens instead is a gravitational ballet. The two galaxies pass through each other, their gravitational fields distorting each disk into tidal tails and bridges of stars, stretching hundreds of thousands of light-years. The encounter launches enormous quantities of gas into star formation, producing a burst of new stellar births across both systems. Then the galaxies swing apart, loop back, and merge again on a second pass. Over billions of years and multiple passes, they settle into a single elliptical galaxy. Simulations of the merger run extensively by multiple teams predict a consistent outcome. After the final merger, the combined galaxy will be a large elliptical structure, mostly red and aging stars with little remaining gas for star formation, orbited by the remnants of both galaxies' satellite populations. The central black holes of both galaxies will eventually spiral together and merge in a cataclysmic event, releasing gravitational waves detectable across much of the observable universe. Our star's position in the final merged galaxy is impossible to predict precisely. Simulations suggest a small but real probability it could be ejected into the outer halo of the remnant, far from the galactic center it currently orbits. More likely, it remains somewhere inside the merged structure, surrounded by stars from two formerly separate galaxies. But the Milky Way and Andromeda are not falling toward each other in isolation. Both galaxies are themselves being pulled in a particular direction through space, pulled towards something enormous. Our galaxy is not sitting still between galaxies. The entire local group, the Milky Way, Andromeda, and all their satellite galaxies combined, is moving through space at roughly 1,400,000 miles per hour, toward a concentration of mass so enormous it bends the flow of galaxies across hundreds of millions of light-years. This structure is called the Great Attractor, and for several decades, its true nature was hidden behind the plane of our own galaxy. The motion was discovered in the 1980s when surveys of galaxy velocities revealed that the Milky Way and thousands of other galaxies nearby were streaming in a common direction, all moving toward a region in the sky near the constellations Centaurus and Norma. The streaming was too coherent and too large to be explained by local gravitational concentrations. Something far away and far more massive was pulling on a grand scale. The Great Attractor itself turned out to be a supercluster of galaxies, centered on a region roughly 250 million light-years away. The dominant structure is called the Norma cluster, a dense concentration of thousands of galaxies. But mapping what lies behind it proved difficult for decades, because it sits almost exactly in the direction of the Milky Way's densest disk regions from our perspective. Dust, gas, and stellar crowding in our own galaxy blocked the view in optical and infrared wavelengths for years. Radio and X-ray surveys eventually pierced the obstruction. Behind our galactic plane, astronomers found an even larger structure than anticipated. The Norma cluster is itself part of a broader supercluster system, called the Laniakea supercluster, a structure identified in 2014 that spans roughly 500 million light-years and contains the mass of 100 million billion stars. The Milky Way sits on the outer edge of Laniakea, in a tendril far from the supercluster's dense core. The Great Attractor is pulling us, but so is an even more distant structure called the Shapley supercluster, roughly 700 million light-years away, which exerts a gravitational influence strong enough to shape the flow of matter across a significant fraction of the observable universe. Our motion through space is the sum of multiple gravitational influences operating on vastly different scales. Here is the most striking implication. The Milky Way has never been in a fixed location. Its position in the universe has been changing continuously as it falls towards successive gravitational concentrations. Where the galaxy sits today, and where it will be billions of years from now, is the result of gravitational dynamics playing out on scales that dwarf the galaxy itself, and the specific region of the universe we currently occupy, the cosmic neighborhood immediately surrounding the local group, turns out to be one of the stranger addresses in the universe, emptier than average, underrepresented in galaxies, on the boundary of a void that may have shaped the Milky Way's entire development. Pull back far enough from the Milky Way and the structure of the universe comes into focus. Galaxies do not distribute evenly through space. They cluster into filaments and walls, dense threads and sheets of matter surrounding vast empty regions called voids. These voids can span hundreds of millions of light-years. Inside them, galaxies are rare or absent. The matter that might have formed them was swept to the edges by the same gravitational dynamics that built the great filaments. The local group sits on the edge of one of these voids. The structure surrounding our galaxy on the larger scale is called the local void, a region of below-average galaxy density, extending several hundred million light-years in the direction of the Hercules constellation from our perspective. The local group is not inside the void but adjacent to it, positioned on its boundary, where the density transitions from the emptiness of the void interior to the slightly denser filament network connecting to larger structures. This position has consequences for the Milky Way's history and for measurements we make from inside it. Voids are not passive empty regions. They exert a kind of anti-gravity effect on surrounding matter. The underdensity inside a void means that matter near the boundary is pulled more strongly toward the denser filaments on the other side than toward the near-empty interior. Effectively, the void pushes matter away from itself. The local group is being repelled from the local void. At the same time, it is being attracted toward the Virgo cluster and ultimately the Great Attractor. The combined effect of this attraction and repulsion shapes the peculiar velocity of the Milky Way, the component of its motion that cannot be explained by the expansion of the universe alone. The galaxy is moving through space in response to the push and pull of enormous under- and overdense structures. Its specific path through the universe is a solution to a gravitational equation written across hundreds of millions of light-years. There is a second implication for cosmology specifically. One of the most pressing debates in modern physics involves the Hubble tension, a disagreement between different measurements of how fast the universe is expanding. Measurements made from within the local universe, using nearby standard candles and galaxy distances, consistently find a higher expansion rate than measurements made from the cosmic microwave background, looking across the full observable universe. The discrepancy is statistically significant and has not gone away with improved data. Some researchers have proposed that the Milky Way's position near the boundary of a void influences local expansion rate measurements. A void environment has slightly different dynamics than the cosmic average. If the local universe is genuinely underdense compared to the mean, local measurements of the expansion rate may be biased high. This does not fully resolve the Hubble tension on its own, but the Milky Way's position on the edge of a void is a confirmed factor that enters the discussion. The void also connects to a much larger structure that remained entirely hidden until just a few years ago. invisible from inside the Milky Way, lurking on the other side of our own galactic disk. In 2020, a team of astronomers announced the discovery of one of the largest structures in the known universe, a vast wall of galaxies, hundreds of millions of light years long, containing tens of thousands of galaxies organized into a coherent sheet of large-scale structure. They called it the South Pole Wall, and it had been hidden from view for decades behind the disk of our own galaxy. The zone of avoidance is what astronomers call the region of the sky directly along the Milky Way's disk. In that direction, the density of stars, gas, and dust in our own galaxy is so high that extragalactic objects behind it are heavily obscured. Optical telescopes looking in that direction see only our galaxy's own material. The universe beyond the disk in those directions was largely invisible to surveys that relied on visible light. The South Pole Wall lies partly behind this obscured zone. Mapping it required techniques that could penetrate the galactic plane, radio surveys tracking the 21-centimeter emission of neutral hydrogen, infrared surveys using wavelengths less blocked by dust, and spectroscopic redshift surveys finding galaxies at high galactic latitudes on either side of the obscured strip, and then connecting them across the gap. The resulting map revealed a structure comparable in size to the Sloan Great Wall, one of the largest known galaxy concentrations. The South Pole Wall spans roughly 700 million light-years in its longest dimension, forming a curved sheet of enhanced galaxy density at a distance of roughly 600 million light-years from the Milky Way. Its full extent has likely still not been mapped, because part of it remains behind the galactic plane. The South Pole Wall is not pulling on the local group with anywhere near the strength of the Great Attractor. At that distance, its gravitational influence on our local motion is modest, but its existence illustrates a broader point about how much of the universe's large-scale structure was invisible to us until recently, not because of the limits of our telescopes, but because we are embedded inside a galaxy that blocks our view of a significant fraction of the sky. The discovery also confirmed that large-scale structure continues on scales well above what earlier surveys had captured. Every generation of survey finds larger structures than the previous generation thought existed. The question of whether there is a scale above which the universe becomes truly smooth and uniform, the homogeneity scale, keeps getting pushed to larger values with each new discovery. Our galaxy sits inside this structure, pulled and pushed by concentrations it cannot see, moving through space, shaped by walls and voids distributed across distances that dwarf any individual galaxy by a factor of millions. And measuring the specifics of that motion from inside the Milky Way is itself contributing to one of the most significant unresolved crises in modern physics. Every cosmologist in the world is currently dealing with a number that will not behave. The Hubble constant, the value that describes how fast the universe is expanding, should be a single number. Measure it one way, you get one answer. Measure it another way, you get a different answer. The two answers disagree by enough that random error cannot explain the gap. And the Milky Way's location in the universe sits directly at the center of the problem. Two methods dominate the measurement debate. The first uses the cosmic microwave background radiation, the afterglow of the Big Bang, combined with a standard model of cosmology to calculate what the expansion rate should be today given the conditions in the early universe. This method, based on observations by the Planck satellite, gives a value of around 67 kilometers per second per megaparsec. The second method uses a distance ladder built from observations inside and near the Milky Way. It starts with Cepheid variable stars, pulsating stars whose brightness cycles are directly tied to their true luminosity, making them reliable distance markers. Measure Cepheids in the Milky Way to calibrate their properties. Use those properties to measure Cepheids in nearby galaxies. Use those galaxies to calibrate Type Ia supernovas, which are bright enough to measure across billions of light years. Use the supernovas to measure the expansion rate directly. This method, associated extensively with work led by Adam Rees and collaborators, consistently gives a value of around 73 kilometers per second per megaparsec. 67 versus 73. The gap is roughly 8 to 10%. At the current level of measurement precision, the probability that this is a statistical accident is extremely small. The gap is real. The Hubble tension is one of the most discussed problems in cosmology today. The Milky Way enters this story at the calibration end of the distance ladder. Cepheid stars in the Milky Way provide the foundational run. Gaia satellite data has measured distances to thousands of Milky Way Cepheids with extraordinary precision, tightening the calibration. The distance ladder measurements have been checked, rechecked, and independently reproduced. The high value holds. Several proposed solutions exist. One class of proposals modifies the early universe physics, introducing new forms of energy or changes to the behavior of the cosmological constant before recombination. Another class questions whether systematic errors in the distance ladder are being underestimated. A third possibility, taken seriously by a subset of cosmologists, involves new physics operating on small scales or late-time modifications to gravity that the standard model does not include. What is confirmed? Both measurements are internally consistent within their own methods. The tension is real. What is unknown? Whether it points to new physics, systematic errors, or both. The galaxy we live in is the foundation of one of the most important measurement chains in cosmology. The precision of Milky Way observations directly shapes our understanding of the universe's expansion history. A galaxy full of strange, active, disturbed phenomena is also the instrument we rely on to measure the cosmos. And everything we have discussed, every star, every stream, every wave and bubble and shell, represents only the fraction of the Milky Way that we can actually detect. Every star you have ever seen in the night sky, every photograph of a nebula, every mapped spiral arm, every stellar stream, every gas cloud, every planet in every system across the entire galaxy. All of it combined accounts for less than 5% of the Milky Way's total mass and energy content. The remaining 95% is invisible to every telescope ever built. Dark matter makes up roughly 27% of the universe's total energy content and constitutes approximately 85% of the Milky Way's mass. We infer its presence from gravity. We see its effects in rotation curves, in the bending of light around galaxies, in the large-scale structure of the universe, in the lopsidedness of our own halo, in the slowdown of the galactic bar. Its gravitational signature is everywhere. The particle itself has never been directly detected. Dark energy is stranger still. It constitutes roughly 68% of the universe's total energy content and is responsible for the accelerating expansion of space itself. Unlike dark matter, dark energy does not cluster. It does not concentrate in galaxies or around structures. It fills space uniformly, exerting a repulsive pressure that pushes the universe apart on large scales. Within the Milky Way, on galaxy scales, its effect is negligible compared to the gravitational forces holding the galaxy together. But on the scale of the universe's expansion, it dominates everything. The ordinary matter, the protons and neutrons and electrons making up every star, planet, gas cloud, and living organism, constitutes approximately 5% of the universe's total energy content, a small minority. And even within that 5%, most of the ordinary matter in the universe is not in stars. It is in diffuse gas, spread through the cosmic web and through galaxy halos, too thin to have collapsed into stars, and too widespread to observe easily. The stars themselves, every burning, fusing, light-producing object in the universe, account for only a fraction of the ordinary matter fraction. The visible light-producing universe is a thin skin on top of an enormous invisible structure. This breakdown is confirmed by independent lines of evidence: galaxy rotation curves, gravitational lensing, Big Bang nucleosynthesis predictions for the ordinary matter fraction, cosmic microwave background measurements, and large-scale structure surveys all converge on the same proportions. The numbers are not in serious dispute. What they mean conceptually is harder to absorb. The Milky Way as we know it, the object of study throughout this entire story, its spiraling arms, its warped disk, its lopsided halo, its ancient stars, its cannibalized satellites, its ringing outer disk, its violent center, its Fermi bubbles, its magnetic field, its mystery signals, all of it is a small, luminous trace on top of a structure we cannot see, made of material we cannot identify, sitting inside a universe driven by an energy we cannot explain. The visible galaxy is the evidence. The full galaxy is still largely a mystery, and both the evidence and the mystery are pointing toward a future already written in the physics of the cosmos. Everything ends, galaxies included. The Milky Way's future is not uncertain in its broad outline. Physics and gravity and time have already determined the sequence of events waiting ahead. The timeline is enormous by human standards, but it is finite. And when you trace the trajectory forward, the galaxy we call home is on a path towards transformation so complete that nothing recognizable will remain. The nearest major event on the timeline is the merger with Andromeda. In roughly 4.5 billion years, the two galaxies will begin their first close pass. Over the following few billion years, they will swing through multiple encounters, each pass distorting both galaxies gravitationally, stretching tidal tails of stars across millions of light years, triggering bursts of star formation as gas clouds collide and compress. The merged remnant, sometimes called Milky Way, will be an elliptical galaxy, a smooth, rounded structure without spiral arms, dominated by aging red and orange stars. The final coalescence of the two central black holes will release gravitational waves detectable across enormous distances. The event will be among the most energetic in the local universe since the Big Bang. The black holes themselves will merge into a single, far more massive object, sitting at the center of the new elliptical galaxy. Our star faces its own timeline. In roughly 5 billion years, it will exhaust the hydrogen fuel at its core and expand into a red giant, engulfing the inner planets. Whether Earth survives this expansion is uncertain. Its orbit may drift outward slightly as the star loses mass, potentially just enough to escape direct engulfment. What is certain is that the inner solar system becomes uninhabitable long before the star reaches its maximum size, as its luminosity increases gradually over the coming billions of years. After the red giant phase, our star will shed its outer layers as a planetary nebula and collapse into a white dwarf, a dense, slowly cooling remnant about the size of Earth, with no ongoing fusion. That white dwarf will cool over trillions of years, fading through orange, red, and eventually black as it approaches thermodynamic equilibrium with the surrounding cosmos. On much longer timescales, the merged galaxy loses stars to gravitational interactions over hundreds of billions of years. Two stars passing close enough exchange energy, one gaining enough to escape the galaxy entirely, the other falling inward. Over enormous timescales, this process, called two-body relaxation, gradually evaporates the galaxy's outer regions, while driving mass inward toward the central black hole. In roughly 10 to the 19 years, most stellar remnants in the galaxy will have either escaped or fallen into the black hole. The protons, in ordinary matter, may eventually decay, on timescales so vast that the age of the universe today is a rounding error. If proton decay occurs at the timescales predicted by some extensions of the standard model of particle physics, ordinary matter itself ceases to exist on those timescales, leaving only black holes and their eventual evaporation through Hawking radiation. The Milky Way's story, across its full timeline, runs from the earliest galaxies forming in the dark of the early universe, through its current active phase of disturbance and discovery, through merger and transformation, through the slow fading of its stars, to the final dispersal of matter into a universe growing colder and emptier with every passing eon. We live at a specific moment in that timeline. The galaxy is alive around us right now, warping, ringing, feeding, glowing, crackling with magnetic fields and mystery signals, and the gravitational push of a neighbor already close enough to deform our halo. We are inside the story, and the story, it turns out, is far stranger than it looked from the outside.